a few years ago, like a decade or so ago, or more, 15 years ago, people, had recognized, of course, that there was a physics case for using positron, a Jefferson lab. And the first thing that they did was to do a proof of concept experiment, the so-called PEPO, polarized electron polarized positron, meaning you make polarized positron by using an IZ target, tungsten. You send your electrons on it. By Strahlungs, they generate a photon, circularly polarized photon, which then decays into E plus E minus, and you pick up the E plus, that's your positron, and it's polarized. With some caveats that I will explain. It's polarized, but not fully polarized. So we did that in the injector years ago as a proof of concept. It was installed, briefly in the injector cave, and that time we generated a positron that 60% polarized, 8 MeV. So not 123. We didn't accelerate it, but that then led people to start organizing workshops where not just accelerator physicists, but of course, nuclear scientists came together to start building a physics case, which eventually led to a white paper about all the physics you could do with a positron beam. So as I showed in the first slides, there are several areas of physics you can explore. They are described in that white paper, and they led, of course, to proposals in front of the pack. Many of them, being approved. So we currently have on the book about 3 years of approved physics. Here we have about 3 years of approved physics of running just with physics experiments that are using positron. We don't have the positron beam yet, but we are ready for it. We have all the experiment worked out. So let's go through some of these. And that is one of the very interesting things that came out of JLab years ago. So people were measuring the ratio of G over GM, the electric to magnetic form factors. And you can do it 2 different ways when you measure this. Initially, people were doing that using what's called Rosenblatt separation, where you, and I will show you in the equation, you can see that you can extract, if you vary the beam energy and the position of your spectrometers, you can extract G and GM, and then do the ratio mu GE over GM, and it's around 1. At least that's what people thought back then. And many measurements were done here at JLab using this Rosenblatt separation technique. Those are the points you see that are near 1. But what you can also measure it using a direct polarization transfer measurement. So that's a point you see in red and blue. And when people started doing that, they realized there is a discrepancy, a significant discrepancy, obviously, between measuring the polarization transfer on the proton or measuring it's happening in this reaction, elastic scattering of a proton. If the cross section for this is what you see on top here. GE, GM, and then you have kinematical factors. The epsilon here is a kinematical factor. That's what you vary when you do the Rosenblatt separation. You vary the beam energy, you vary the spectrometer positions, your kinematics, and you fit, and the slope is GE, and the intercept is GM. That works until you get to IOQ squared, where it is discrepant with the energy, with the polarization transfer measurement, which is the formula in the bottom. And the current thinking, initially people were thinking maybe it's a experimental problem, the way we extract. Did we control the errors correctly in the extraction? Is it a relative correction? we did more accurate measurement. Most of that was settled, and now the consensus is that it's likely two-photon effect, which is the fact that this formula here, the left part, it's just the Born approximation, the one-photon exchange. If you take into account diagrams like those where you have two-photon or more, then you start having extra terms in your cross-section or even in the polarization transfer that are parameterized in terms of those new functions that are not very well understood theoretically. There are various models. It's model dependent, significantly model dependent, and that's the reason for the discrepancy. We think is these terms, and so there are experiments that are proposing to measure that with positron, because it turns out that you can see right here that if you measure with electrons and positron, the sign flips both in the cross section and the polarization transfer. So you can access, these extra terms independently, so you can do a clean extraction. This is really important to nail that down because it has consequences not just for the form factors, but it has consequences for the experiment, because those two-photon or multi-photon effects or photon effects, they are corrections in many experiments, and if you don't understand that very well, then it's a problem. So there is a huge program that's going to look at this two different ways. We're going to redo measurements. So what I should say is that the plot I showed you that shows those clean measurements, it was done in 2 steps. At first, people were doing this Rosenblatt methods, right? As I said, you vary the kinematics to scan for a given q squared, or the virtual photon, q squared, to scan the cross section, and you plot and you fit and you get G and GM. A fixed q squared is the cross section depend linearly, but because of the fact that G is suppressed by 1 over q squared at higher q squared, it's become less and less accurate for higher q squared, so it's difficult to control. So people came up with this great idea of super Rosenblatts, which that's how those measurements there wasn't done. So I will show you in a second what super Rosenblatts is. But that was measured. It's an experiment, JLab, E0101, those black points here. And when people remeasured, so super Rosenblatt, instead of detecting the electron, you detect the struck proton, the elastic proton. And if you detect the proton, you can do, I'll show you why, much more accurate measurement. And so after we did that, people were still puzzled at that time because it's now confirming, the Rosenblatt measurement, and it's still discrepant with the direct polarization measurement. The direct polarization measurements, they are done when they were done before in OLE, in OLC. You take the scattered proton and you put it through an analyzer, meaning another nuclear target, that will generate an azimuthal asymmetry that you measure, and this polarization is proportional to that. We have a focal plane polarimeter, for example, in OLE that we used successfully to do those measurements. There is still a discrepancy. So let me first show you how does this work. So if you detect the electron, the regular Rosenblatts, so the curve on the top left here is momentum versus, you scan in epsilon, right, when you do your Rosenblatts. The momentum of the objects, like, for example, the electron, which is in dashed. You see it varies significantly as you scan for given q-squared beam. This means you have to make corrections, momentum-dependent correction in your detectors, or things like that. And this affects the accuracy of your measurement and your extraction. On top of this, the cross-section at low epsilon is smaller if you detect, if you look at the reaction from the point of view of detecting the electron versus the proton, is the top right plot. So that leads to more correction even, because now to be able to measure the cross-section at low epsilon, you have to crank up the current. If you crank up the current, you have current-dependent correction, for example, target boiling or things like that. That are, or just measuring the current, it's things that are difficult to gauge properly. Now, if the bottom plot just show you the sensitivity of the Rosenblatt separation or the super Rosenblatt on not knowing very well the incoming energy of the beam or the angle. As you can see for the electron, this is in percent, right? That's an error in your experiment, right? The systematic. For the electron, it's much bigger than for the proton. The reason being that the proton momentum is nearly constant for a given q squared, whereas the electron is not. So you end up with much better accuracy when you detect a proton, when you do super Rosenblatts, than when you detect the electron. And you are less sensitive to systematics like knowledge of the beam incoming energy. You're also less sensitive to systematics like the incoming, reconstructing the incoming angle. So that was published in 2005, I believe, the first experiment using super Rosenblatt. It was done a few years before, and that's what is going to be used, of course, for future experiment. In particular, there are experiments that are being proposed to redo all of that, but with positron, because of those signs, right? With positron and a clean separation, we should be able to extract those terms very accurately. Okay. So there is one that's proposed in all B, for example, in class 12, 50 nanoamp beam with slight modification to the detector to detect the lepton in the central detector. They will have a pretty good kinematic coverage. As you can see, epsilon versus q squared there. And they will be able to scan the epsilon dependence and the q squared dependence. There are also polarization, direct polarization measurements that are also, there is a letter of intent that is going to be at some point a proposal to actually do those direct polarization measurement with positron. This is a slide from Mark Jones that showed back then what they had done, right? As I was mentioning earlier, this at that time was, a very good result at Jefferson Lab. It was it's a very famous piece of physics. It was done in the 90s, right? We did it several times, and that's the principle of how the spectrometer works. You send your scattered proton through an analyzer, meaning a nuclear target, I think CH2 it is, and they will generate an asymmetry, azimuthal asymmetry. You measure that, and you can get polarization. Now, so that's for the two-photon effect. It's interesting also to measure the two-photon effect because they show up in deep inelastic processes as well. And if we can understand how this works in the elastic process, and we can use some of that knowledge for two-photon or soft-photon, multi-photon exchange. Now, another big area of research at Jefferson Lab is nuclear structure. The well-known one right now is DVCS. There is also VCS, which VCS is when you scatter very close to elastic, right? A lepton onto a proton, and then you detect the scattered electron and photon. So it's near low energy regime. It's a small t, meaning the whole momentum transfer between the ingoing and outgoing proton is very small. And when you measure the cross section of these processes, you end up with something like that, which is it's never by itself. There is an interference term with beta Hassler, which is when you emit photon on the incoming or outgoing electron. And this kinematically is the same as the VCS process, pretty close, so it interferes with it, right? So you end up with interference term, d int. It has both an imaginary and a real part, d int and d tilde intens, and then the VCS term and beta Hassler term. We know to calculate the beta Hassler, but if we use, so in the past, we've done many measurements in the VCS regime, not just the Jefferson lab, but also in Europe, like MAMI in Germany. And those were also important experiments. And what you measure there is it was studied, as early as, I think, the early 50. If you're at sufficiently low energy, you can expand the spin-dependent part into a multiple expansion. The first moment is anomalous magnetic moment, and then you have all those extra multiple terms that we call generalized polarizability. Typically, they show up in the cross-section as azimuthal dependence, sine phi, sine 2 phi, cos 2 phi, and so on, and combinations of it. And that's how you extract them. This phi angle I'm referring to is the angle between the two planes, the incoming plane, electron, proton, the outgoing plane, the VCS photon and proton. They have a phi angle. And this, when you do the analysis, you exploit the fact that the generalized polarizability will show up as azimuthal dependence. So you can extract individual polarizability. Now, if you use positron, you get new observables, which is very exciting, that some of them are particularly sensitive to specific polarizability, like, for example, the electric dipole, A tilde VCS. And you do that by doing, for example, beam charge asymmetry measurement or beam spin asymmetry measurement. So beam charge asymmetry measurement is when you do the difference of the sum over the sum of the rates for electron and positron in the cross section. And the beam, so no polarization. And the beam spin asymmetry is when you have a polarized beam, transversely polarized, and you do the difference between the rates for left and right helicity for positron and electron. And you end up with being able to build quantities like this. Let's see, I have it like this. It's the same in DVCS. See the rate, y plus, plus y minus, minus. So you build those directly from your measurements, and you can relate that to certain terms in the VCS cross-section that we could not access before because we didn't have positron. So there is a letter of intent for this. An experimental scenario for this is under study. A similar related subject is when you go to the Bjorken limit, the DVCS, larger T, full momentum transfer. When I mean T, of course, I mean the full momentum transfer here, right? Between the, in DVCS, you also have interference with the beta Hassler, and you can also write the cross-section this way. And you can do a number of experiments where and we did many DVCS measurements here at JLab with polarized electron beam, where you can access what's called generalized pattern distribution, because the fact that you have momentum transfer T, you also have two vertices between the virtual photon. So it's a virtual photon that coupled with a pattern inside the nucleus, and then eventually it emits a real photon, a VCS photon. In between, there is momentum transfer, is called psi. And so you now can map out the nuclear structure with 3 variables instead of 2. You can do X Bjorken, which is a fractional momentum carried by that pattern you are striking. You can do Xi, which is in between the 2 vertices, and then Q squared, or you can do X Bjorken T, Q squared, and so on. And those are GPDs. Those GPDs, if you integrate them, you get back to known structure functions like G1, G2, F1, F2, and some moles, many. It's incredibly rich what you can do with that. there is a number of combinations. So this slide is a little complicated, but there is a number of combinations you can build depending on whether you using electron or positron, what you are doing polarized or unpolarized, or doing averaged. Some part of the cross section flip with the sign of the particle. Some part of the cross section there when there is polarization. So if you do the right measurements, you can extract all of those things or many of those things, and you end up with GPDs trying to map them out. So what GPDs are, it's a generalization, right? They capture they give you an idea of the internal dynamics in the hadron, right? Like the distribution of forces, the distribution of the angular momentum, the distribution of correlation between spatial and longitudinal, correlation in the spin and the quarks, the distribution. So here is on that slide, CH and E, they are GPD, so there is three variables in it: X Bjorken, the Xi, and then a third variable, and T. And if you integrate them, you can recover some well-known other factors. All sorts of things you can do with it. This is a very fertile field of nuclear structure. It's basically tomography of the hadron. For example, you can look at pressure inside a proton, the third graph at the bottom, which gives you an idea of the internal pressure in a proton. You can do flavor separation if you measure on positron and neutron targets. You can look at the impact parameter and look at this, which gives you the valence quark versus the C quark, the distribution in the hadron, and many other things. The field is still being extremely active. It's one of the main area of research here at JLab, and it can only be enriched by using a positron beam, because you can start building those quantities. So for example, if you use unpolarized beam charge asymmetry, which is this one, you're sensitive to the real part of the quantum form factors, which are integral of the GPD. If you use a polarized beam, you can build these quantities that, again, you measure that from your rate detector that's sensitive to the imaginary part, and you can build all sorts of quantity. You can build this one, which is a charge average beam spin asymmetry, and that's sensitive to the higher twist effect in the hadron. So there is proposals, of course, that are being put to do exactly those measurements. Eric Voutier and company are proposing, for example, this one in class 12, where they are going to measure all those quantities, and there are some others. Now, this is not the end of the story. We already have, as I said, 3 years of physics experiments stacked up with positron, but people are still thinking about all the interesting things they could do, right? And there are lots of area of physics you can do. For example, DVCS of the neutron, coherent DVCS, incoherent DVCS. So what is incoherent DVCS is when you tag the outgoing proton on top of the photon, and it's a semi-inclusive. We are at large T, and you have a nuclear target like helium-4, for example, and you allow for your reaction to include not an outgoing proton and outgoing photon, but other stuff that you don't measure, right? And that's the incoherent DVCS. You can do double DVCS of the proton in the solid detector, for example. So double DVCS is when your DVCS photon then decays in mu plus, mu minus. The solid detector will have means by which they can detect the muon. So that's another experiment that could be done. You can do DVCS of polarized target, it's much harder in a 4-pi detector like class for practical reason. We do helium-3 polarized experiment in OLE, and that's not that simple because you need a cylindrical field and high Tesla around it and a glass target and so on. But people are trying to figure out if that's possible because it's incredibly rich in terms of the physics you can do. So that there is active investigation about this. I should mention also that the incoherent DVCS, it's interesting for several reasons, but one of them is the EMC effect, the fact that particles, the scattered particle, as they cross the nuclear medium, they can be accelerated or decelerated in the Coulomb field of your nucleus. And it's a well-known effect that has been known since the 50s or 60s or something like that, but never was nailed down very, very cleanly. There is an opportunity if you do DVCS of a nuclear target to investigate maybe the EMC effect. Class already saw signs, already isolated the incoherent DVCS channel in their data stream when they were doing coherent DVCS. If they saw it in, I think, in G6. So we know it's there. What those experiments that have been proposed in the future is to use a positron, right, to further enrich them. But we know we can detect that and we can tag it, and so that's very interesting. Then there is electroweak physics, challenging experiments usually because of the cross sections, and you measure asymmetries usually. Actual form factors of the proton, deep elastic on the strangeness content of the nucleon. There are various proposals at that stage. Most of them are letter of intent rather than proposals. People are still working out how to do some of these things. And again, this obviously this list is not exhaustive, right? That's what people are currently thinking about. But if you come up with a genius idea of something else that's not on the list, just do it and write a letter of intent, and it will be considered, right? Fun thing, well, I find that fun because it's not, you wouldn't think it's a classic thing we do at JLab, is a dark matter production. So it has implication, of course, in astrophysics, right? But so dark matter is a fact that there might be a dark photon, a boson that is that decays into light dark matter particles that are not detectable. And if you can generate this A prime, it's called A prime, several different ways. One way is to use a tick target. So what's been proposed at JLab here is to send a positron beam through a tick target, and then the positron interacts with the atomic electrons, right, in your target. And there are diagrams like that. E plus, E minus produce a prime, right? And that A prime then decays into light dark matter particles that can be detected. So what your signature is in this kind of experiment is if you have missing energy, you have calorimeter right after you target, and you tally up everything that coming out of reaction. And if you can't and you find missing energy, then that's your signal. Interestingly enough, that has been measured, well, not really measured. We haven't found, nobody has found yet, dark matter particles, but what people have done with various experiments, some of those experiments are neutrino experiment. Some of them are experiment that are in colliders like Babar. But they put upper limits, right, on the mass or bounds. So on the horizontal axis would be the mass of this light object that decays from the A prime. And on the vertical axis is a parameter that shows up in those theoretical models. That's usually what people use to quantify the sensitivity of the experiment to the dark matter. It's a ratio of the Xi over the A prime times some kinematical factor. And as you can see, it has been mapped out by JLab as a unique opportunity to seriously constrain this if that particle happen to be in this regime, in this region. If it is, we get a Nobel Prize for sure. If it's not, we get the opportunity to put a beautiful bond, right? Much tighter bond on it, right? So it's a gambit, right? Because of course, we're not covering the whole thing, right? We're covering a specific region. Now there are reasons why theorists think that it might be a good region, right? So this experiment is being proposed, so we can place bonds, on the mass of this light dark matter particle. Whether or not we find it, who knows? This requires Higgs charge, so time structure, but we know to do that. 31 megahertz beam. I was telling you earlier, 499 megahertz is usually how we generate the rep rate for the accelerator. You can adjust it to something else for more bunch charge, like 31 megahertz. As a matter of fact, we ran like that for years for the G0 experiment. We are running at high bunch charge, 31 megahertz. So we know to do that. So, and it takes. There are other proposals that have to do with actual neutron current coupling. Some of these are have been published already in terms of letter of intent or proposals even, but as far as I know, it hasn't yet been approved by the PAC. One of them was deferred, not because it's a bad experiment, but because further information is needed. People need to do further calculation to get it approved. The timeline I was discussing earlier is, again, that's stuff you guys will do, not people like me, or maybe, but maybe not. So we are here, right? Molar founded. We are starting it next year. Then there is a science review for solid going on, and then we'll build solid. Meanwhile, we build the positron source, and we work on the 22 GeV CBAF. We upgrade the first part, which is we build the transport to go from the earth where we make those positron to CBAF. There's transport lines we're going to build. Meanwhile, people keep working on the 22 GeV. We run the positron program here, 35, 36, 37, and then stop and install the 22 GeV upgrade and then run the 22 GeV upgrade. As you can see, you always have to do projections decades ahead, right? Whether that turns out to be exactly that, nobody knows. But you need to have a plan to start with when you're talking about major investments and major efforts, right? So that summarizes how it's going to work. As I said, we're going to make the positron in here. It's true for the 22 GeV CBAF. We'll make the electrons there, 650 MeV. Then we build a beamline that we dig a tunnel that goes from here to here, and then we hang magnets on the ceiling of the existing accelerator tunnel. Like we are not changing we still want to maintain the machine right up to pass 5, as I said earlier, because you accelerate with FFA arcs. So we have a new beamline that's going to hang on the ceiling all the way, same thing in the arc, and then we inject the beam in the front there, and then we accelerate to 11 GeV for positron. And if it's an electron beam to 22, for positron, what we have to do, obviously, is flip all the polarities of the magnet, right? So we have a plan to do that. All the dipole, instead of, if you want them to bend right, so we have to flip the magnetic field because now you have positron, right? But that's well understood, obviously, so it's part of the plan. We're going to generate different positron beam. Not just, so we're going to generate two kinds of positron beam. The unpolarized positron beam and polarized positron beam. It's easier to make, in terms of beam intensity, to make them unpolarized. I will show you why. It has to do with the kinematics of the process. There is a direct correlation between polarization and momentum at which you pick the positron that's emitted from the decay of the photon. So we'll provide is a polarized or unpolarized positron. We also provide a degraded electron beam from the LERF. So we'll make a beam that looks as bad, so to speak, in terms of phase space, right, as the positron beam, so that to take into account systematics for experiments, they would want to run many experiments. They will run with the electron. Then we'll swap to positron. It'll take a week or so to swap polarities and everything, and then run with positron. To minimize your systematics, you want as many things are the same as possible other than the charge of the particle. So we can make degraded electrons that looks, in terms of phase space, the same as positron and from the LERF. So that's the other thing. And then, of course, we can still make regular electron in the regular CBAF. So this process where you scatter your electron beam on a tungsten target generates, positrons that are longitudinally polarized, but you have to make a cut. So if you plot the yield, the positron polarization versus the incoming electron energy and the yield, you find that the optimal in terms of polarization is to if you use an electron beam to hit your tungsten target to make your positrons at 120 MeV, you would want to capture your positron around 60 after that to get the maximum polarization. If on the other hand, you want as many positrons as possible and you don't care if they have polarization, you can select them at lower momentum where it's high yield of the cross section, and that's the unpolarized mode. So we have to design this so that it can be reconfigured to either produce polarized positron at lower yield or unpolarized positron at high yield. It has to do with how you select the positron. So that's how in practice it's going to be laid out in that LERF building. We need a high current electron gun because of the cross sections, right? You hit with an electron that makes a photon, which itself decays in a positron and electron. You lose a factor of 1,000 or so in current, right? So you need a milliamp of electron to make a microamp of positron. So you need to make a gun that can do a milliamp for long periods of time. So there's currently research going on. We are developing that gun. We are then accelerating this electron to 123, hitting that production target. We make the positron, then we have a number of things here to collect that positron. It's emitted in a very large opening angle, by the way, so it's not that easy. So you need solenoids to grab it immediately. Then you need a warm RF to accelerate it to condition the longitudinal phase space. Then you need, a variety of things, right? It's called the capture section to grab that positron as much as you can. You want to grab as much as you can, but it's difficult to grab all of them because they're emitted in a very large opening angle. Then you accelerate them, you condition them. You have a spin rotator similar to the Vince filter we have in the CBAF machine. We will have a spin rotator in here so that we can, again, orient the spin of the positron so that it gets oriented the right way when it gets into the hole. And then it's sent out of this building and it goes through that tunnel I just showed and gets in the main machine and then accelerated. So to do that, we have a R&D group, many people working on that. We have some people working on that electron gun. We have people working on the collection system. We had a PhD already, somebody, not Andre. Andre is a staff, but we had somebody who did this PhD just on how you collect positron, right? Because it's not a simple problem, right? He just graduated. We're collaborating with the industry. Part of the way you finance these projects is the DOE has grants for collaborating with industry, SBIR, small business industry. And so Valkostrom, for example, has a little research company, and we're collaborating with him and his colleagues to study. There's two different options for the target. You can do is a solid target, tungsten, rotating target so it doesn't melt. And a liquid target, liquid gallium. I mean, some interesting stuff, and that's what Val is studying. So we have people working on those two concepts, designing. We're going to build a prototype target to see if that works. I mean, to work out the bugs, we know it should work, but collection system, and then I would transport large beam because they're bigger than the electron beam. This is what an electron gun looks like. It's similar to the one that's in CBAF, right? So that's what it looks like. It has a cathode, as I said, and an anode. And so this is the gun here with a feed for the high power. Then there is, you can see some feed, that's a vacuum pump, some feed for the lasers, and then one way to insert the cathode, load it in it. When you want to make to reach higher voltage in your beam, you need a bigger anode because of, otherwise you have high voltage shorts. It's a very difficult problem, by the way. Those things have to be in, I think it's SF6, fluoride gas, SF6, so that you reduce the probability that you will have shorts, discharge. It's state-of-the-art stuff. We have run the existing CBAF at 1 million before, but the problem is the quantum efficiency doesn't hold. It dies after a few days, right? You can run full out, and after a few days, you need to stop and reset your cathode. So the bulk of the research is towards trying to build a gun that will do 1 million, but you won't have to stop physics every 2 days, right? You want the thing to last for several weeks, or 2 weeks at least. So that's what my colleague Carlos Hernandez and his group are doing. So here's a plot, you were interested in the QE earlier. That's a plot of the QE over time. You need larger electrodes, of course, because to get a larger spot, you have to put a larger spot on the cathode to spread all this charge. To get high current, you need more charge, and that depletes your quantum efficiency. So one way is you have bigger cathodes, so they are installed in what's called a puck, which is the holding mechanism for those cathodes. So that's going on. So that's all and lastly, we are collaborating with Japan, actually, with a company in Japan to develop insulators, high voltage. All of that is, challenging, right, in terms of high voltage. So there is no easily commercially available solutions. We had to customize commercially available stuff, and that doesn't work too well. So we are collaborating with, I think it's Kyocera, one of those Japanese high-tech company to design that just for us, and then it'll be used by others. But so I power tungsten target. Andrei Yushakov is working on that together with Silvio Kovrig from nuclear physics group, target group. Silvio is doing all the calculation and simulation for the magnetohydrodynamic in the target and thermal dynamics, and so is Andrei. They are working together. It's difficult to design these targets because you're depositing quite a bit of energy in it. You have to be able to cool it enough so that it doesn't melt, but it has to rotate, and so now you have to design a large chunk of tungsten that's rotating at 2 Hertz and with water channels in it, and then you have to worry about issues of radiation damage, fatigue, mechanical fatigue, stress, all those things. That's the practical, right? When it's applied physics, when we're trying to make something like that, you run into all sorts of hurdles that you'd think, well, that's easy. Here's a chunk of tungsten, I push my beam on it, and I'm good to go. No, it's much more complicated than that, which is in part makes it interesting to work on because you get to learn about all sorts of physics to do one project, right? Mechanical, thermal stuff, physics, energy deposition stuff, all sorts of different areas of physics to make it work. Also, around this target, as I told you earlier, you have to grab those positrons as soon as possible. So there is a solenoid right on there. So now you have to insulate all of that. So to shield all of that from radiation, so that you don't destroy your solenoid with all that. You're pushing a beam there, depositing kilowatts in that target, and it's shooting all sorts of particles, not just positron and electron, and you have to cool all of that. And so yeah, we are absorbing 115 kilowatts out of 123. So it's challenging. So that's currently been, so as I said, we're going to build a prototype to test all that stuff, a smaller prototype with a smaller energy, a smaller beam that will test at the LERF. We're also prototyping that solenoid. We calculated the field maps, in Tosca, and then we use Fluka to push a simulation with all the particles, right, to see if that works, because that target, that solenoid on the target also has absorbers for to absorb to deposit the particles. So all of that is being simulated. As I said, we have testing with a liquid target, gallium indium arsenide, liquid metal that you pump, and then you hit the beam on that that laminar flow of gallium arsenide. It's challenging because you want to obtain a laminar flow, so that's magneto-hydrodynamic, very complicated. People are prototyping this. You have to prototype how your nozzle should be to produce that laminar flow and so on. And all that is going on with a separate group. Transporting large beam, the transverse emittance of that, the extent of that beam in transverse is much bigger, many times that of CBAF when you generate it. The goal is to be able to inject it in front of the North Linac, to accelerate it. And so the transport line have to be dedicated with large quads, low dispersion optics, and so on. That's currently being worked on. We developed this part of the transport, that's on the ceiling, using a concept that's being used for light source, DBA, dimple binochromat, to be able to do that. This quad has been prototyped. I'm accelerating because we getting late. That's going to be built because we can use this for both the Positron project, but also will work for the 22G VCBAF. So we can do that and do both at the same time. This degrader, we're installing it in the injector. We're installing a device that will allow us to insert what do you call that? Chunks of metal. Well, not a chunk, it's a small foil of various thickness into the electron beam, so that we can artificially, create scattering, right? Multiple scattering, and produce a bigger beam so that we can mimic what a positron beam would be in terms of phase space. So we can, even without positron already test, if we can transport that in the main Linac. That's been installed this summer. Of course, it's such that you can retract it. Obviously, when you do regular physics, you don't want to destroy your beam, but for testing purpose, we'll be able to do those tests. And that's been, again, it's going to be installed, so it has been prototyped, and the mechanical engineering design has been done. Those magnets, we have to reverse the polarity to be able to transport positron, about 1900 correctors and quad, but they're already bipolar, the power supply, so it's just a set point. You just type a different number and you're good to go. But many of those dipoles, they are unipolar, so they need to be rewired so that we can easily flip the field. That has implication in terms of performance of those magnet, saturation of the iron in the magnet, depending on which side of the hysteresis curve you are. So that's been studied, but we think it should be doable. In order to, the lab, of course, is supporting this project. We also aggressively seeking funding and getting funding from external sources like typical FOAs, funding calls from a DOE. You can apply and get money if your project, is deemed interesting. You can also do the SBIR. We also have lab-directed research fund, LDRDs, that maybe some of you applied already for. You can apply for LDRDs for anything, right? Theoretical physics, nuclear physics, constructing stuff. It's a fraction of the budget of Jefferson Lab every year is set aside. It's mandated by the DOE. I don't remember what the percentage is, but it's a percentage of the total budget. And there is a committee at the lab that then can allocate that money for your project. So you can, if you have an interesting idea, typically it's on the scale of a few $100,000. You can apply and get funding, which is great, especially for young scientists when you're getting started finding funding. It's not always easy, and that's a great way to get started. If you have a good idea, you can present it, at the LDRD every year and get awarded the LDRD and start your research. Okay, so that's where we are in the Positron projects. It's a group of about 20 or so people actively working on the design of it, but of course, a number of people interested in it. If you include nuclear scientists, it's hundreds, right? We have those workshops every year, and it's a very active field. Patricia will discuss tomorrow the 22 GeV physics, which also is encompassing a lot of things and very rich, right? And lots of people are interested in that too. It's natural extension to Jefferson Lab 12 GeV. Many of the experiments when at 12 GeV, there's natural extension at 22. And so both projects are actively pursued. And that's, how we see the future of Jefferson Lab in terms of upgrading the machine. Any questions? Yeah.
For the positron beam, well, for one of the observables, you mentioned that I believe that for one of the new observables related to the positron beam and electron beam, it uses both measurements.
Beam charge asymmetry, yes.
Yeah. So would it so data for that specific observable would be collected. So would it be in the same run that you would have a positron beam?
Well, yes and no.
Stop for a while, flip.
Exactly.
Electron beam?
Right. Yeah, exactly. So we cannot flip, instantly, right, from electron to positron, but that's exactly what would happen. We would run in electron configuration, take the data. Ideally, you would want to do that during the same period, which is, you finish taking your data for electron, then you spend a few days. So there are discussions about how long it takes, right, to flip from positron to electron. Ideally, if we can do it in a week or less, that's the current target. You flip, and then you retake your data with positron, and now you have the two data sets. So it does imply that you need to control things like acceptance or things like that, accurately, right? You want the things to be the same so you can then combine them. So the closer in time they are when you take the data, the better it is. But yes, you will have to, take the data and separately.
I want to ask about the targets. I know you mentioned like a liquid and a solid target.
Yeah.
What are proposed materials, or what would be something?
Right. So for the solid target, it's tungsten. IZ. So you want an IZ target, right, to produce as many of those Brandstein photon as possible, which then they can positron. So it's tungsten for the solid target, and for the liquid target, it's a gallium indium arsenide.
Questions?
So in these dark matter, like dark photon exclusion plots that you showed, is there a reason why the JLab experiment sort of plateaus right around, what's it, like 70, 50 MeVs designed to do that, or is it?
Well, it has to do with the kinematics that we can reach, right?
Right. So it's designed to plateau there. What's like Yeah, what's the reason for that? Is that the most likely dark photon mass, or?
No, it's because, again, that's what, if you do the math, right, and figure out what we can do with the beams that we have and the kinematical reach that we have is where we land.
Oh, okay, so it's
We
constrained
can't
by.
easily, we
Yeah.
can't easily go measure like, here or here. It's that.
No, but it's really based on the setup and not on, say, let's say we want to measure specifically this.
The
mass.
shape of that, yes.
Yeah, okay.
Yves, is there any chance after you install this new accelerator for the 22 GeV beam, is there any chance to turn then the machine into any plus and minus collider?
Unlikely, because you would have to have a separate machine to make the E plus, right? Because right now the plan is to use the same machine to either make E minus or E plus. We also can't make E plus to go to 22 because we're using permanent magnet and it would be the wrong polarity. So no, very unlikely that you'd be able to do that.
Not even making the two beams circulate at the same time in this.
So we looked at many of those options, and there is no easy solution above 11 GeV. Again, because of the design that shouldn't of the FFA to do that. Of course, it is not to say that people aren't scratching their head to see what they could do, but so far we haven't found a solution that would work, and that would be within the budget, right?
Well, more questions. Come on, guys. Let's engage, ask questions. Don't be shy. Oh, sorry. Oh, okay.
Could you please go to the slide where you show the deviation of the form factors from like at high Q squared values?
This one.
No,
one of
I think
them,
it was
yeah.
before this. Like the,
Well, the same, but this one was upgraded. Yeah, this
yeah,
one.
yeah.
Oops, sorry.
So, like what values of Q squared would you say that it starts to deviate?
Above 3 or 4, that of course you can debate what the exact number is, but typically above Q squared or 3 or 4.
Yeah, so as far as I know, like JLab has the ability of 12 GeV for quite some time, right?
Yeah.
So if I exclude two-photon exchange here, what are the other possibilities that might explain it? And
So-
what possibilities we already know that?
Oh, no, we already tried to do that. I mean, we did all those measurements, right? And the only, the other possibility would be, for example, the sensitivity of your extraction, right, to experimental errors at IQ squared. As I said, it's harder and harder to do resemblance because GE shrinks and that's the slope of your extraction. And so initially people were thinking exactly that. Then they thought maybe it's momentum corrections, maybe it's relative correction, and we control all of that now. So the only candidate that's left is a two-photon exchange, and it's different as I showed. It's because it shows up differently in the polarization transfer measurement that it does in the cross section. So you end up with this difference.
So like this is the only theoretical candidate that we have at the moment.
I think so, yes, as far as I know.
Okay, thank you.
Please, I have one question.
1 second, you're next.
I think there was a recent paper released in March.
Gravitational, gluonic, oh, sorry. I think it's good. But, it's the battery. You can just ask.
Should I just shout?
Yeah, okay.
I think there was a recent paper that was released in this March about the gluonic gravitational form factors of the proton. I think that's done in OLA. So they're kind of extracted from GPDs, right?
Yes.
Is this relevant to that program as well?
So yes, not this slide, but some of the GPDs indeed are sensitive to gravitational form factor, and some of the DVCS process You may be able to access some of that. I'm not familiar with that particular paper, so I can't tell you for sure, but definitely it's in the GPDs, yes.
Wants to add to that.
So that particular paper did not actually extract the GPDs.
Yeah, I know they didn't, but it was the idea that was presented.
Mhm.
They said the solid detector would greatly improve the measurements, I think.
Possibly. The extraction of GPDs from experimental data is actually really difficult.
So you remember when you extract GPDs, you have a third variable. So you're basically doing the tomography, which means that you open up, you need a lot more phase space, right, to be able to measure all of that, and it's very difficult to do. And that's the challenge, right?
That's also planned for the EIC.
That's more likely to be done there, yes.
So right now you're working on a gun for the injector, right? So why are you only using one gun? Why not use two?
Well, that's an excellent question, actually. That was considered. So to make more current, I mean, either you crank up the current in your one gun, or you do a Gatling gun type of, arrangement, right? Which indeed was considered, right, for different projects, but also for this, for positron. If we can't make a milliamp, we just make 10 guns, 200 microns, we combine them together and we're good to go. It's expensive, but it's technically possible. People were considering that for other projects, like the accelerator-driven system from years ago.
So why not more than one gun?
Because it's technically more complicated and expensive. And if we can do without having to do that, then we're better off, right? It's also an extra possible point of failure, right? Now, that was proposed in other experiment to actually reduce the failure rate. It was like you would have, multiple guns that you would switch instantly from one to the other. It's for those accelerator-driven system where you use a beam to excite a nuclear reactor to make energy, and it's in subcritical. So if you turn the beam off, the reactor doesn't run, right? But for that to work, it's incredible. It needs to be 99.99% uptime. You don't want more than a few minutes per year of downtime. That was the plan, which is very difficult to achieve. So people came up with the idea of having multiple guns that would switch, kind of like fault tolerant system for computers, for example, where you switch. But I don't know of many places that are using multiple guns combined together to make one beam, because it adds complication.
Yes, madam, I had a question. My internet was disturbing a little, if you permit me
Yeah,
to ask my
please.
question. My question was, if, Professor, you take also in consideration the eventual electromagnetic resonance which could happen during the interaction between electrons and positrons, or any particles which will be interacting during these collisions inside the new apparatus.
I'm not sure I understand the question.
Can you repeat again, Fabian?
My question is, when they will finish to insert this new apparatus in the CBAF, if the eventual electromagnetic resonance which could happen between the different particle and antiparticle which will collide together inside will be taken in consideration.
I'm not sure what that is, but they won't be together in any case, right? We are either doing electron or positron. We're not sending electron and positron together. Now, of course, if you refer to the fact that electron and positron can combine together and make photons, or the reverse process, yes, we use that to actually produce them, right? So, but I'm not aware of any other consideration.
Does that
Then
answer your
then you neglect then we neglect the electromagnetic resonance which could happen after.
Yeah, I'm not sure I understand. You would have to email me more details so I can understand what you are getting at.
Okay.
I don't know.
Okay. Any more questions?
So, how does getting a positron beam help us with TPE?
With,
How does getting a positron beam help us with TPE?
oh, it does, because if you do the measurement with electron and then positron, there is a sign flip in the cross sections.
So,
So you can isolate the, so see right here, look at the cross section.
right.
As a sign flip between electron and positron, so you do the measurement, do the difference over the sum, and you can isolate this part that's TPE. And you can do the same thing in the direct polarization transfer. There is a term that changes sign. So that's why you want, you know, to do that.
So it basically allows us to separate the TPE part
Yep.
like more easily.
Exactly, yeah, by comparing E plus and E minus.
All right, I think we can, let's first thank Yves again. I think we can call it a day, and I'll see you all tomorrow. First, thank you so much. It was really nice getting to meet you all. And I'll see you tomorrow at 9 a.m. here for the first lectures on lattice QCD.